Today I'll talk about small data, so the opposite of what everybody else is talking about today. So what is small actually? So my boss, when there was still big data was a thing, I used to say that big data are defined as data that is so big that it causes problems. In this, traversing this definition, you may say that small data is big data is not big, right? It's troublesome because of being small, not being big. And the question that arises quickly is that why is it still a thing? It's 2019, and is it so hard to get more data? And actually, there are some arguments that this is still valid, and the first thing is that things usually start small. So if you start analyzing anything, the first data you will get will be small, usually, at least. The other thing is that, well, some things can be acquired at low cost, and some not so much. The measurements cost money, cost time, cost lives, sometimes even human lives. And data sets also like to grow in a wrong direction. We don't get more observations, we get observations that are more complex, which actually makes the number of observations effectively smaller. And the other thing is that we sometimes have big data, a large amount of data, but we are actually interested in a subsample of this that is very rare. And so if we multiply this by this, we get something that is small. We get a small sample from a very big population, which is interesting. And what are the problems of all of this talk summarized in 3 points? So the first thing is that estimations works poor. Even if we have consistent estimators, they work for infinite samples, and with the in the border on the other side, we are getting bad performance. Also, the sampling is hard to get right. If you get a bunch of data from minimal sources, the biases start to disappear. If you're trying to get few points, it's very hard to get this right. And also, obviously, the imputation have a huge impact. If you have a hole in a small data, this hole will be effectively larger than a big data. And probably the most problematic thing that is not fundamental is that humans love to draw conclusions from small data. They don't like to analyze big data. They want small data because they think they can comprehend them easily, and the psychology for 30 years collecting tons of examples that humans are terrible at doing statistics, and they also feel very confident about their wrong statistical decisions. So that's a thing that must be analyzed. So how does it look like in the machine learning view? So I'll sketch a interpretation of machine learning that's not analytical, that's algebraic. So we have those observations, and the observation is some state. There's a discrete state. That state space may be giant, but everything that fits in the computer is finite, so it's actually discrete. And we have some decision, and for modeling we are estimating what is the probability that each observation state is of a class, one of those Y states. And this is obviously easy, and when we have many samples of each observation, then the decision is clearly sampled, and we can estimate this, and the opposite of this condition is the small data stuff. And yet, we expect machine learning to answer in every possible condition. So even for unsampled states, we expect some answer, and this answer must come from somewhere, and what it comes from, where it comes from, the method itself, So this is where the selection of the method really matters. Right? Because what the method can say, it can say that there is nothing, that it knows nothing, or it can use some other states to interpolate the result. And here is this option for this machine learning supremacy over the statistical analysis, that it can somehow interpolate this using the actual invariants that are in the data. So here, like, we have a model that actually understands the data, right? And it can make some useful decisions that are over this simple framework. Right, so what are the enlargement strategies for having small data? Like, what can we do to have it larger? Like, and the most popular idea is something called augmentation. It's very known, so I won't talk about it much. Right? And the idea is that we can apply transformations that we expect are meaningless, right? So if we want to identify a number that is that shouldn't depend on how this number is oriented in space, like we can just get a bunch of numbers and then permute everything by rotating, and like think that our model will be also better, and because we have suggested this invariance harder. So like I won't talk about this. The second idea is observation pruning, right? Because smallness is exponentially relative to the information content. So if we can prune the observation, like the smallness will go out. And the final thing is re-encoding, right? So we can sometimes have some additional information or assumptions, some domain knowledge or something like that. And we can use it to re-encode the observation in a way that this information is exposed, right? So it can be partially this, can be other thing, and like this also helps methods to like dig in deeper and extract better information. Right, so let's sneak into this second option, like to prune information, and this is a simple case study. Like here we have 3 old machine learning methods, random forest, SVM, and a single classification tree. We have some data set with like various number of cases, 20, 50, 100, and 200, and we have also various number of features, 15, 100, 500, 1000, and 5000. And what we do here is that like we build a model, we test it on an independent set, right? And we are trying to optimize the set of features so that the accuracy will be maximal on this test set, obviously. And so we get decent improvement. And like, what's the problem here? The problem here is that this data is just a bunch of noise, right? There's nothing to be learned here. So what we get here, this improvement, is only an overfitting over feature selection, right? So like this is an example that like this is not really an optimization problem, right? Because you can optimize everything to even make perfect predictions from nothing. Yeah, so why is it a problem? And actually, if we can dig into the theory of feature selection, we know that there are 2 types of non-necessary information in the data sets, right? Because we have information that is irrelevant, which is does not depend on our decision and are independent. So this is clearly irrelevant, and we can clearly remove it. And the other part of this non-necessary information is the redundant information, which is somewhat relevant, so it's not irrelevant, but it is duplicated, right? So we have few copies of the same information. And obviously, this way we can just go on with 1 copy of this information, so we can theoretically also kick it out. So yeah, the removal of relevance alone is exponentially hard, it turns out, because we must look at every possible combination of information. Right, and the removal of both is actually very easy, like, because if there is a unique bias classifier, It only needs, like, so this is the most perfect method that is like unapproachable, but it will always work best. We only need the rest of information, so non-relevant, so non-irrelevant, and non-redundant. Well, yeah, but the problem that arises here is that we have to have a unique model, and this is a very simple logical data set. Like we have two values, 5 independent values. They have these values of 0 and 1 in all possible combinations, and we have A, all B, A and B, not A, and we have the decision which is XOR of A and B. And so those are clearly relevant. And like there is a bunch of sets of relevant features here, and they are clearly redundant, and we can make alternative models like from this and this, or with this and this and this and this that will solve this problem. So there is an ambiguous solution, so everything is redundant, so completely nothing is strongly relevant, and this way, like with optimization, we cannot solve the problem and we always remove everything. Like so, it goes worse because in small world it's easy to get spurious interactions. So the interactions that come only from noise, and they can become effectively equally ambivalent than this actual solution. So yeah, obviously the breaking some tie is easy. Like there is literature on feature selection says that it's not a problem because like every time we have some noise, and this noise will always break the tie. Like, but now there is a probability that like if we have a spurious solution and a good solution, like we can break the tie randomly, and now we have a 1 in 2 chance of finding something useful and finding something nonsense. Like that. So, and also if we focus on some solution, the overall process will be less robust, because if it breaks, like there's no other option. Right? So we can visualize it like this structure with columns, and there's a question, well, what columns here are irrelevant, right? We can remove any of them without much trouble, but like we don't know which. Like they are equally good, and we can start removing too much, and it will all start to collapse. Right? So, and even though they are all redundant, like they are making the structure more stiffer, so like that's why it's more robust. Okay, so how can we do this pruning safer? And the answer to this question is that like we can use some all relevant selection methods, right, which as I said was close to impossible, but there are some heuristics, and like the heuristic I was involved in is called Boruta. It's an actual algorithm. So like when you go to the theory of information, you get a nice notion of what is a relevant feature, and it turns out that a relevant feature has some non-zero conditional mutual information, while conditioned on some subset of other features. Right? So we can just use this formula to solve the problem of relevance. Like, so the first problem is that like the estimation is usually inflated by noise. Like, so we'll get false positives, and to this end we can use like permutation test, add some nonsense, shadow features, as we call them, and use it as a datum to remove this. The other problem is that estimating information, mutual information, is hard, so we are using here in the original version random forest for that. As it turns out, the random forest importer is actually an estimator of mutual information. So there's the theorem for that. And so, okay, anyhow, this will be all unstable, you may say, and that's why we iterate a lot, and we obviously get a slow algorithm, but it can be, like, it's not that slow on small data for one point, and you can also use some faster important sources, which is maybe not as bad as this, but faster. And this is an example how does it work. This is on a data set from the NIPS conference 2003 feature selection challenge. It's called Modelon. It has 20 relevant features. And what you can see here is that the importance of all features as the algorithm goes on. And it's those greens are the relevant, and you can see that one feature is in this buff of non-relevant ones, and while the algorithm removes them, it gets rescued and returned. Okay, so that's the first part, and that is something old, and now something new. Focus on this recoding stuff. So like I was saying that I like this information theory approach, and there are many nice methods based on the Shannon entropy, but it requires categorical data, as we all know. Like there is this differential entropy, but it does not hold some important properties which enable some methods. So like big data can be easily discretized. You can get some categorical data, cut them, and have continuous data, cut them, and have categorical. But small, not so much, and anyhow this adds hyperparameters. How do we do this? So like precise values often also matter less than we care. Like usually if we make some analysis, we often normalize data, we often detrend them, so we are actually removing actual values, and still this discretized version will actually look into it too much. So can we do better? Can we make continuous data categorical in a better way? And the solution I propose is something that I called Kendall transform. It's actually connected with the Kendall correlation, that's hence the name. It's a small vector that's continuous. We can make a matrix of the relation between each of its elements. We can also now unfold this relation like this. This means that this is bigger than this. This means that this is smaller than this. Yeah, for equality, we have the equal third state, and we have now n times n minus 1 ternary values. And like this, this transformation rescues the Kendall correlation, which is like the normalized number of the equal signs when compared with two transformed values. Also, the mutual information is now the function of the Kendall correlation, so it's it rescues the original idea, but what's good is that we can now freely use the full potential of the information feature selection. And here's the example that we can use joint information between A and B, in those to uncover the relation between Y, A, and B in those two forms. So this is a linear match, and we can see that this joint state is always better than the importance of each of the A and B. So this is linear regression, so why bother? You can see that it equally works with this more crazy function. Here's the joint, here's the B, which goes down because it's this is more pronounced, obviously, so it also has this nice interpretation. Here's the example of some true data. This is the effect of morphine on the various chemicals in the brain of the rat. And what you can see here is that points are colored according to the Boruta decision, for instance, as a golden standard. Here you have this binned mutual information, and you can see that it generates a lot of false positives, and this one is on its own without analyzing it, any interactions, is actually reproduces Boruta very nicely. Okay, it also has this nice property that it eats ties by those square states, equal states, and the funny thing is that if you start adding ties, you will end up in a categorical binary decision, and it turns out that actually it converts mutual information in a function of this area under rock curve. So as you may know, this is also a statistics of Mann-Whitney-Wilcoxon test, so it's a cool thing that you have this continuous transition from analyzing something which is basically a correlation and non-parametric correlation, you end up in a test of like a group inequality. And like obviously it comes for the price, like it does not consider things that are not monotonic functions. So like you cannot solve square if the input is symmetric over 0. Okay. Yes. So it also introduces some certain structures. So like you have to be careful when using certain methods like Baruta, like because like this will get broken if you don't retain the structure, but this can be fixed easily. Okay, so I don't know how to deal with non-binary categorical features yet, like, because and also the size of the transformed data explodes fast, so it's probably only for small data. So here are the takeaways of my talk. Like this, we have to usually use a lot of analysis of small data, so it's like good to know a few things about them. Like so, machine learning actually I think helps very much with such data. But we must use approaches that are capable of saying no, like in this example of the nonsense data there. Baruta says that nothing is important, and every optimizer will say that something is. Right? So also the feature selection is pretty dangerous. Like this, all relevant is a good thing to use. And like we have also a way how to treat small continuous data. And that's the end of my talk. So you can find Baruta on Cran, and it's also a Python version. This is my package that actually does some information science, so it will have this Kendall transformed soon, so ready to use. So thank you very much.